Stan Gibilisco here to describe a polar coordinate system that I devised way back when I was in high school to help me understand infinity from a graphical standpoint. I called it a compressed polar coordinate system, or infinitesimal polar coordinates, with two S's rather than one in this word, so that it means having to do with infinity instead of vanishingly small. Just a little aside there. But this is a conventional polar coordinate system that has been squashed geometrically according to the radius. The angles are all the same. Here we have the radius r and the angle theta going counterclockwise from a reference axis. Here is the reference axis. Theta in radians, 0, pi over 2, pi, and 2 pi radians in a full circle. Remember that pi over 2 radians equals 90 degrees, and 1 radian is just a little more than 57 degrees. So the only difference between this system, infinitesimal polar coordinates, and the conventional polar coordinate system is the compression of the radius in such a way so that 1 is halfway between 0 and infinity, 2 is halfway between 1 and infinity, 3 is halfway between 2 and infinity, and so on and so on and so on, so that you never really get all the way to this dashed circle, which represents a radius equal to infinity. That's what that dashed circle represents. Now let's just suppose that we decide we want to graph a function in this system, and let's make that function very simple. Let's suppose we say that r equals theta over 2 pi. R equals theta over 2 pi. If we do that, then one complete revolution will bring us out to 1 radius. So if we go around 2 pi radians, we'll get out to r equals 1. 2 pi over 2 pi equals 1. If we go around again, we'll get out to 2. So we get a spiral, just sort of like the conventional spiral of Archimedes. I believe that's called a spiral of Archimedes, isn't it? It's a spiral where the radius is a constant function of the angle. Now in this case, we can go beyond 2 pi radians to get our radii. 4 pi radians is 2 full revolutions. 6 pi radians is 3 full revolutions. And in general, n pi radians is n over 2 full circles. So if we keep going and going and going, we're going to get this spiral that expands, but it gets closer and closer to this dashed circle, but never quite gets there all the way. Now, suppose that instead we took something more like a conventional coordinate system and made a graph of this. And I believe, as a matter of fact, I have a conventional coordinate system here in this file, in this bunch of files. So I can, now this is actually a directional H-plane directional polar grid for ham radio antennas, but you can get the general drift. We have degrees here instead of radians, but the spiral in a case like this might go out 1, 2, 3, 4, and keep expanding forever, because there's no boundary here. We can't see all the way to infinity on this particular graph. However, we can if we go back to this graph. we can see all the way to infinity in a certain sense. Now, what happens to this spiral if we imagine that it actually reaches this dashed line? Then we have r equals infinity, and theta equals, well, we might say that theta equals infinity as well, because, after all, infinity divided by 2 pi is infinity, right? So when theta equals infinity, there is no defined angle associated with it. It could be any angle. But if we want to just deal with one full circle and express angles as partial circles, then we could say that in this sense, infinity, in the angular sense, is sort of like a numerical entity whose value is at least 0 but less than 2 pi, one complete circle. A numerical entity, that is to say, a number that can attain all of the values greater than or equal to 0 but less than 2 pi at the same time. Now, if you want to read more about numerical entities, I believe I express some theory of numerical entities in my Nerd Cave Hypotheses. Just type my website, sciencewriter.net, and then NCH. So that's the deal here with this polar coordinate system that can show the entire plane in a finite area. And it does, in fact, map all of the points in this finite circle to an infinitely expansive plane. Stan Gibilisco signing off. Until next time, so long.